Imagine a world twice the size of Jupiter, spinning silently through the void between star systems. No sun rises or sets on this frozen realm. No seasons change. For millions of years, it has wandered alone through the galaxy, ejected from its birth system by gravitational forces so violent they sent it careening into interstellar space at speeds of up to 50 kilometers per second. This isn't science fiction, it's the reality of rogue planets. And according to recent estimates from NASA's Nancy Grace Roman Space Telescope team, there may be more of these orphaned worlds drifting through our galaxy than there are stars. The numbers are staggering. In 2021, astronomers using gravitational microlensing data calculated that for every star in the Milky Way, there could be anywhere from 1 to thousands of these wandering planets. If we take the conservative estimate of just one rogue planet per star, we're looking at over 400 billion homeless worlds in our galaxy alone. But here's what makes this discovery truly remarkable. We've only directly confirmed the existence of a handful of these cosmic wanderers, and each detection represents a triumph of observational astronomy over nearly impossible odds. Today, we're going to explore one of the most haunting phenomena in astronomy: planets that have been cast out from their stellar families to drift through the darkness of space. We'll examine how these worlds form, how they're ejected from their systems, and what their existence tells us about the violent early history of planetary systems throughout the galaxy. We'll also investigate the cutting-edge techniques astronomers use to detect objects that emit virtually no light, and we'll consider whether some of these rogue worlds might harbor the conditions necessary for life, even in the depths of interstellar space. The story of rogue planets begins with understanding planetary formation itself. In the early stages of any star system, gravity pulls together dust and gas into a rotating disk around a young star. Within this disk, small particles collide and stick together, gradually building up into larger and larger objects. First comes dust grains, then pebbles, then asteroids, and eventually full-sized planets. But this process is far from gentle or orderly. As these protoplanets grow, they begin to interact gravitationally with one another, and these interactions can become catastrophic. Computer simulations of early planetary system evolution reveal a period that astronomers call the Late Heavy Bombardment, a time when gravitational interactions between forming planets were so violent that objects were regularly flung out of their systems entirely. During this chaotic phase, which likely occurred in our own solar system about 4 billion years ago, planets migrate inward and outward from their original orbits, sometimes approaching dangerously close to one another. When two massive objects pass within a certain distance, one of several things can happen. They might collide and merge, they might settle into a stable orbital configuration, or one might receive such a powerful gravitational kick that it escapes the star's influence entirely. The physics behind planetary ejection follows what's known as the three-body problem in celestial mechanics. When you have two planets orbiting a star, their gravitational interactions with each other and with the star create a complex dance that can remain stable for billions of years. But add a third massive body to the equation, or allow the orbits to become highly elliptical, and the system can quickly become unstable. The mathematics describing these interactions were first worked out by Henri Poincaré in the late 19th century, and they show that even tiny perturbations in such systems can lead to dramatically different outcomes, what we now recognize as chaotic behavior. In practical terms, this means that during the early evolution of a planetary system, a close encounter between two forming planets can result in one being accelerated to escape velocity, while the other remains bound to the star. The planet that receives the gravitational kick becomes a rogue, while its former companion may end up in a highly elliptical orbit or even spiral into the star. These ejection events are incredibly violent. The forces involved are comparable to those that would tear apart a moon or asteroid, yet somehow planets manage to survive them intact and continue their journey through space. The first theoretical predictions of rogue planets emerged in the 1990s, as computer models of planetary formation became sophisticated enough to track the fates of individual objects through millions of years of evolution. Astronomers like Sean Raymond at the Observatory of Bordeaux and David Bennett at Notre Dame began running simulations that showed ejection events were not rare exceptions, but rather a natural and inevitable consequence of planetary formation. Their models predicted that every star system should produce at least as many rogue planets as bound planets, and possibly many more. But predicting the existence of rogue planets and actually finding them are two very different challenges. These objects emit virtually no light of their own. They're not stars, so they don't undergo nuclear fusion, and they're too far from any star to reflect significant amounts of light. For comparison, imagine trying to spot a basketball floating in the middle of the Pacific Ocean on a moonless night, using only a flashlight from the shore of California. The task seems impossible, and for many years, it essentially was. The breakthrough came with the development of gravitational microlensing as an observational technique. This method relies on Einstein's theory of general relativity, which predicts that massive objects bend space-time around them, acting like gravitational lenses. When a rogue planet passes between Earth and a distant background star, its gravity focuses and amplifies the star's light for a brief period, typically lasting from hours to weeks. By carefully monitoring millions of background stars and looking for these temporary brightening events, astronomers can infer the presence of otherwise invisible objects. The optical gravitational lensing experiment, known as OGLE, has been the pioneer in this field. Operating from Las Campanas Observatory in Chile since 1992, OGLE monitors about 200 million stars in our galaxy's central regions, looking for microlensing events. The project has detected thousands of these events, but distinguishing between those caused by rogue planets and those caused by bound planets, brown dwarfs, or low-mass stars requires careful analysis of the light curves, the pattern of how the star's brightness changes over time. In 2011, OGLE and the Microlensing Observations in Astrophysics Collaboration announced the first statistical evidence for a large population of rogue planets. They had identified 10 microlensing events with durations too short to be caused by stars or brown dwarfs, but consistent with Jupiter mass objects. Extrapolating from this small sample, they estimated that Jupiter mass rogue planets might outnumber main sequence stars in our galaxy by a factor of 2. This was the first direct observational evidence that the theoretical predictions might be correct. The significance of this discovery extends far beyond simply adding more objects to our catalogue of cosmic phenomena. Rogue planets represent a fundamentally different class of world from anything we see in our own solar system. They exist in an environment where the temperature is determined not by stellar radiation, but by the planet's internal heat generation and the cosmic microwave background radiation, the afterglow of the Big Bang, which provides a baseline temperature of about 2.7 Kelvin, or negative 270 degrees Celsius. For a rogue planet to maintain any surface warmth, it must generate heat through internal processes. Large planets can retain heat from their formation for billions of years, and they may also generate additional warmth through radioactive decay of elements in their cores. Computer models suggest that a Jupiter-mass rogue planet could maintain a core temperature of several thousand Kelvin for billions of years after ejection, potentially keeping subsurface oceans liquid beneath thick ice crusts. This possibility has profound implications for astrobiology. Here on Earth, we know of ecosystems that thrive around hydrothermal vents on the ocean floor, completely independent of sunlight. These communities are powered by chemosynthesis rather than photosynthesis, deriving energy from chemical reactions rather than stellar radiation. If rogue planets can maintain subsurface oceans through internal heating, they might provide environments where similar life forms could evolve and persist. The concept becomes even more intriguing when we consider that rogue planets, unlike bound planets, are not subjected to the intense radiation bursts that stars occasionally emit. They're shielded from cosmic rays by any magnetic fields they might possess, and they experience no climate variations due to stellar activity. In some ways, they might provide more stable environments for life than planets orbiting active stars. But detecting potential biosignatures on rogue planets remains far beyond our current technological capabilities. We can barely detect the planets themselves, let alone analyze their atmospheric compositions or surface conditions. However, the James Webb Space Telescope, and future missions like the Nancy Grace Roman Space Telescope may change this situation dramatically. The Roman Space Telescope, scheduled for launch in the mid-2020s, is specifically designed to conduct the most comprehensive survey of rogue planets ever attempted. Using gravitational microlensing, it will monitor hundreds of millions of stars simultaneously, potentially detecting thousands of rogue planet candidates. The mission's wide-field infrared capabilities will allow it to detect objects with masses as small as Mars, providing our first census of low-mass rogue planets. One of the most exciting aspects of the Roman Space Telescope mission is its potential to detect rogue planets in the act of ejection. Computer simulations suggest that planetary ejection events continue to occur throughout the evolution of star systems, not just during their chaotic early phases. Gravitational interactions with passing stars, the evolution of binary star systems, and even interactions with planets that formed much later can all trigger ejection events billions of years after a system's initial formation. Recent observations have provided tantalizing hints that such late-stage ejections might be relatively common. The Gaia space mission, which is mapping the positions and motions of over 1 billion stars in our galaxy, has identified several star systems that appear to have experienced recent gravitational disruptions. Some of these systems show evidence of planets with highly eccentric orbits that may be in the process of being ejected, while others seem to be missing planets that theoretical models suggest should be there. The study of rogue planets also connects to broader questions about the formation and evolution of our own solar system. Numerical simulations of the early solar system consistently predict that our planetary system should have ejected at least one, and possibly several planets during its chaotic early history. Some astronomers have speculated that the unusual orbital characteristics of our outer planets, particularly Neptune's highly inclined orbit and the sparse population of the asteroid belt, might be evidence of ancient ejection events. There's even a hypothesis, proposed by astronomers like Matija Cuk at the SETI Institute, that Earth's large moon might have formed as a consequence of a planetary ejection event. According to this theory, a Mars-sized planet was ejected from the outer solar system early in its history, and its departure caused gravitational perturbations that eventually led to the giant impact that created the moon. While this remains speculative, it illustrates how the study of rogue planets can illuminate the hidden history of our own cosmic neighborhood. The detection methods for rogue planets continue to evolve and improve. In addition to gravitational microlensing, astronomers are developing direct imaging techniques that could potentially spot the thermal emission from warm rogue planets. The upcoming extremely large telescopes, ground-based observatories with mirrors 30 to 40 meters in diameter, will have the sensitivity to detect the faint infrared glow from Jupiter-mass rogue planets within a few hundred light-years of Earth. Direct imaging offers several advantages over microlensing. While microlensing events are one-time occurrences that provide only limited information about the lensing object, direct imaging allows for detailed spectroscopic analysis. This means astronomers could potentially study the atmospheric compositions of rogue planets, determine their rotation rates, and even search for moons or ring systems. The possibility of moons around rogue planets opens up another fascinating chapter in this story. Just as planets can be ejected from star systems, moons can potentially survive the ejection process and continue orbiting their parent planets in interstellar space. These hypothetical rogue moons would be even more difficult to detect than rogue planets, but they might provide additional environments where life could potentially exist. Tidal heating from the gravitational interaction between a rogue planet and its moon could provide an additional energy source, similar to what we observe in the Jupiter-Europa system. The constant flexing and stretching of the moon's interior due to tidal forces generates heat that could maintain subsurface oceans even in the absence of stellar radiation. This mechanism has been proposed as a way that moons of rogue planets could remain habitable for billions of years after ejection from their birth systems. The search for rogue planets has also led to improvements in our understanding of planetary formation more generally. The existence of these objects provides a natural laboratory for studying planetary interiors, atmospheric evolution, and thermal physics under extreme conditions. Unlike planets orbiting stars, rogue planets evolve in isolation, making it easier to disentangle the effects of internal processes from external influences. For instance, observations of rogue planets could help resolve long-standing questions about the minimum mass required for deuterium fusion, the process that distinguishes brown dwarf stars from large planets. The boundary between planets and brown dwarfs is currently defined at about 13 Jupiter masses, but this limit is based primarily on theoretical models. Direct observations of isolated objects in this mass range could provide empirical constraints on where to draw the line between planets and failed stars. The study of rogue planets also intersects with research into dark matter and modified theories of gravity. Some of the microlensing events attributed to rogue planets could potentially be caused by primordial black holes, hypothetical objects formed in the early universe that could contribute to dark matter. Distinguishing between these possibilities requires careful analysis of the microlensing light curves and comparison with theoretical predictions for different types of objects. Recent developments in machine learning and artificial intelligence have revolutionized the analysis of microlensing data. Neural networks trained on simulated light curves can now identify potential rogue planet candidates in real time, allowing for rapid follow-up observations. This capability is particularly important because microlensing events are unpredictable and unrepeatable. Once the alignment between the rogue planet and background star is broken, the opportunity for detailed study is lost forever. The MOA collaboration, based at Mount John Observatory in New Zealand, has been at the forefront of developing these automated detection systems. Their algorithms can process thousands of light curves simultaneously, flagging potentially interesting events for human review within hours of their occurrence. This rapid response capability has enabled coordinated observations from multiple telescopes around the world, providing more detailed characterization of rogue planet candidates than ever before. One of the most intriguing aspects of rogue planet research is the possibility that some of these objects might not be true planets at all, but rather sub-brown dwarfs, objects that formed through the collapse of gas clouds rather than through accretion in protoplanetary disks. These planemo objects, as they're sometimes called, would have similar masses to large planets, but very different formation histories and internal structures. Distinguishing between ejected planets and sub-brown dwarfs is challenging with current observational techniques, but it's an important question for understanding both star formation and planet formation processes. Sub-brown dwarfs should have different atmospheric compositions and thermal evolution patterns compared to ejected planets, and future observations may be able to detect these differences. The concept of rogue planets has also influenced our thinking about the prevalence of planetary systems throughout the galaxy. If every star system produces numerous rogue planets during its formation, then planets may be far more common in the universe than we previously thought. This has implications for estimates of potentially habitable worlds and the likelihood of finding life elsewhere in the galaxy. Current models suggest that the Milky Way contains between 100 and 400 billion stars. If each star system produces an average of 2 to 10 rogue planets, then our galaxy could contain over 1 trillion planetary objects, most of them wandering freely through interstellar space rather than orbiting stars. This represents a fundamental shift in how we think about the cosmic census of worlds. The timescales involved in rogue planet evolution are almost incomprehensibly long. Once ejected from their birth systems, these objects continue their journeys through the galaxy for billions or even trillions of years. They may occasionally pass through other star systems, but the vast distances between stars make close encounters extremely rare. Most rogue planets will spend their entire existence in the near vacuum of interstellar space, slowly cooling and evolving in isolation. This isolation makes rogue planets natural laboratories for studying planetary physics under extreme conditions. Without the complex interactions between stellar radiation, atmospheric dynamics, and surface processes that characterize planets in star systems, rogue planets evolve primarily through internal processes. Their thermal evolution, atmospheric escape, and magnetic field generation can be studied without the complications introduced by stellar heating and tidal forces. The Nancy Grace Roman Space Telescope's Rogue Planet Survey is expected to provide unprecedented insights into these processes. By detecting thousands of rogue planets across a range of masses and ages, the mission will enable statistical studies of rogue planet populations for the first time. Astronomers will be able to determine how the frequency of rogue planets depends on stellar mass, metallicity, and galactic location, providing clues about the planetary formation process throughout cosmic history. One particularly exciting possibility is the detection of rogue planets that were ejected relatively recently, within the last few million years. These objects would still be warm from their formation and ejection processes, making them easier to detect with infrared telescopes. Studying young rogue planets could provide direct observational evidence of ongoing planetary system instabilities and help astronomers understand the mechanisms that drive planetary ejection. The search for rogue planets has also motivated the development of new theoretical frameworks for understanding planetary system evolution. Traditional models of planetary formation focused primarily on the end state of the process, the stable planetary systems we observe around mature stars. But the recognition that ejection events are common and important has led to a new emphasis on the dynamical evolution of planetary systems over their entire lifetimes. This broader perspective has revealed that planetary systems are far more dynamic and violent than previously thought. Even apparently stable systems like our own solar system may have experienced dramatic reorganizations in the past, with planets migrating between orbits, colliding with each other, or being ejected entirely. The existence of hot Jupiters, giant planets orbiting extremely close to their stars, is now understood to be a consequence of these dynamical processes. The study of rogue planets also connects to fundamental questions in planetary science about the relationship between planet mass, composition, and formation environment. Earth-mass rogue planets, if they exist in large numbers, would represent a population of terrestrial worlds that formed under very different conditions from the rocky planets we observe in star systems. Understanding how these objects evolve could provide insights into the factors that determine planetary habitability more generally. Recent theoretical work has suggested that some rogue planets might retain substantial atmospheres even after ejection from their birth systems. The key factor is the planet's escape velocity, the minimum speed needed for gas molecules to permanently escape the planet's gravitational field. Large planets have high escape velocities, making it difficult for their atmospheres to escape, even without stellar heating, to drive atmospheric loss. This possibility has led to speculation about super-Earth rogue planets that might maintain dense atmospheres and even surface liquid water through greenhouse heating. While such scenarios require very specific conditions, including the right balance of atmospheric composition, internal heat generation, and thermal insulation, they illustrate the diverse range of environments that rogue planets might provide. The detection of rogue planets has also had unexpected implications for our understanding of stellar formation and evolution. Microlensing surveys designed to find rogue planets have simultaneously discovered populations of free-floating brown dwarfs and low-mass stars that were previously unknown. These objects provide important constraints on the initial mass function, the distribution of masses at which stars form, and help astronomers understand the transition between star formation and planet formation. One of the most remarkable aspects of rogue planet research is how it has changed our perspective on the cosmic environment. For most of human history, we've thought of space as empty, a vast void punctuated by isolated islands of matter in the form of stars and planets. The recognition that interstellar space may be populated by billions of wandering worlds fundamentally challenges this view. Instead of empty space, we now envision a galaxy filled with dark, silent worlds drifting between the stars. These rogue planets represent a hidden component of galactic ecology, objects that carry materials and potentially even life from star system to star system over cosmic timescales. While the probability of any individual rogue planet being captured by a star system is extremely small, over billions of years and across millions of systems, such events may play a role in the transfer of materials and even biological information across the galaxy. The technological challenges involved in studying rogue planets continue to drive innovations in astronomical instrumentation and data analysis. The need to detect tiny, brief changes in stellar brightness has led to the development of extremely precise photometric techniques. The requirement to monitor millions of stars simultaneously has motivated the construction of wide-field survey telescopes with sophisticated automated observation systems. These technological advances have applications far beyond rogue planet research. The same techniques used to detect gravitational microlensing events are being applied to search for exoplanets, study stellar variability, and investigate dark matter. The data processing algorithms developed for microlensing surveys have influenced research in fields ranging from variable star astronomy to gravitational wave detection. Looking toward the future, several next-generation facilities will dramatically expand our ability to study rogue planets. The Vera Rubin Observatory, currently under construction in Chile, will conduct the legacy survey of space and time, monitoring billions of stars for transient events including microlensing. The European Space Agency's Euclid mission, while primarily designed to study dark energy, will also conduct extensive microlensing observations. These surveys will detect tens of thousands of microlensing events, potentially identifying hundreds or thousands of new rogue planet candidates. The statistical power of such large samples will enable detailed studies of rogue planet demographics, including their mass distribution, spatial distribution within the galaxy, and frequency as a function of stellar environment. The combination of improved detection capabilities and theoretical advances is leading to increasingly sophisticated models of rogue planet populations. Modern simulations can track the formation and ejection of planets in realistic stellar environments, accounting for the effects of stellar multiplicity, galactic tides, and encounters with molecular clouds. These models predict not only the total number of rogue planets, but also their detailed properties, including mass distributions, velocity distributions, and thermal evolution histories. Perhaps most remarkably, some of these simulations suggest that a small fraction of rogue planets might eventually be captured by other star systems. This process, known as planetary capture, could redistribute worlds throughout the galaxy over cosmic timescales. Captured rogue planets would likely end up in highly eccentric or retrograde orbits, quite different from planets that formed in situ around their current host stars. The possibility of planetary capture raises intriguing questions about the origins of unusual objects in our own solar system. Some astronomers have speculated that Triton, Neptune's largest moon, might be a captured Kuiper Belt object. Others have suggested that the hypothetical Planet 9, if it exists, might be a captured rogue planet rather than a remnant from our solar system's formation. The study of rogue planets also provides a unique window into the early history of star formation in our galaxy. Because rogue planets preserve a record of the conditions in their birth systems, studying their properties can reveal information about stellar and planetary formation processes that occurred billions of years ago. Different stellar environments produce different types of planetary systems, and the population of rogue planets represents a fossil record of these diverse formation histories. As we continue to discover and study rogue planets, we're gaining new perspectives on some of the most fundamental questions in astronomy. How common are planetary systems? What determines the final architecture of a planetary system? Are there environments beyond traditional habitable zones where life might exist? The answers to these questions have implications not just for our understanding of planetary science, but for our place in the cosmic order. The story of rogue planets is ultimately a story about cosmic violence and survival. These worlds have experienced some of the most catastrophic events possible in planetary evolution. Gravitational encounters so violent that they were literally thrown out of their home systems into the darkness of space. Yet many of them continue to exist, preserving their internal heat and possibly even their potential for habitability over billions of years of isolation. This resilience suggests that planetary environments may be more robust and adaptable than we previously imagined. Life, if it exists on rogue planets, would represent the ultimate triumph of biology over hostile cosmic conditions. Such organisms would need to survive not just the initial ejection event, but millions or billions of years in the near absolute zero of interstellar space, sustained only by internal planetary heat sources. The current state of rogue planet research can be summarized as follows. We have strong theoretical reasons to expect that these objects exist in large numbers, mounting observational evidence that they do indeed populate our galaxy, and rapidly improving technological capabilities to study them in detail. What we lack is a complete census of their properties and a detailed understanding of their formation and evolution processes. The next decade promises to be transformational for rogue planet science. The Nancy Grace Roman Space Telescope alone is expected to discover more rogue planets than all previous surveys combined. The James Webb Space Telescope may be able to characterize the atmospheres of nearby rogue planets detected through direct imaging. Ground-based surveys will continue to expand the statistical sample of microlensing detections. These observational advances will be complemented by theoretical progress in understanding planetary formation and evolution. Improved computer simulations will be able to track the formation of planetary systems in realistic stellar environments, predicting not just the properties of surviving planets, but also the characteristics of those that get ejected. Machine learning techniques will enable the analysis of vast data sets from multiple surveys, potentially revealing subtle patterns and correlations that point toward new physical insights. Perhaps most importantly, the study of rogue planets is beginning to integrate with other fields of astronomy and planetary science. Connections to astrobiology, galactic astronomy, stellar formation, and even cosmology are revealing unexpected links between seemingly disparate phenomena. Rogue planets may play roles in galactic chemical evolution, the transfer of organic materials between star systems, and the long-term fate of planetary atmospheres. The implications extend beyond academic astronomy. Understanding rogue planets could inform our thinking about planetary protection and the long-term survival of technological civilizations. If rogue planets can maintain habitable environments for billions of years, they might represent refuges for life during periods of galactic instability or stellar evolution. Conversely, the recognition that planetary ejection is a common process underscores the dynamic and sometimes hostile nature of planetary system evolution. As we reach the conclusion of our exploration of rogue planets, it's worth reflecting on what these discoveries tell us about the nature of the cosmos. The universe emerges as a place far more dynamic and populated than we might have imagined. Between the stars, in regions we once thought of as empty space, there may be countless worlds pursuing their own evolutionary paths in isolation and darkness. These rogue planets represent one of the most significant discoveries in modern astronomy, not because they challenge our fundamental understanding of physics, but because they reveal aspects of cosmic evolution that were previously hidden from view. They force us to expand our conception of what constitutes a planetary system, what environments might be suitable for life, and how matter and energy flow through the galaxy over cosmic timescales. The story of rogue planets is far from complete. Every new detection raises as many questions as it answers. How did these particular objects form? What are their internal structures? Do they have atmospheres, magnetic fields, or moons? Could they harbor life? How do they interact with the interstellar medium during their long journeys through space? These questions will drive astronomical research for decades to come. They require not just improved observational capabilities, but also new theoretical frameworks for understanding planetary evolution in extreme environments. They demand interdisciplinary collaboration between astronomers, planetary scientists, astrobiologists, and even philosophers grappling with questions about the nature and prevalence of life in the universe. What we can say with confidence is that rogue planets have fundamentally changed our perspective on planetary systems and their evolution. They've revealed that the cosmos is far more violent and dynamic than we previously understood, but also potentially more hospitable to diverse forms of planetary environments than we had dared to imagine. In the darkness between the stars, worlds continue their ancient journeys, carrying with them the secrets of their violent births and the possibilities of futures we can barely comprehend. The next time you look up at the night sky, remember that you're not just seeing stars. Drifting invisibly between those points of light are countless worlds, some perhaps larger than Jupiter, others smaller than Earth, pursuing their solitary paths through the galaxy. They represent one of nature's most remarkable phenomena. Planets without stars, worlds without sunrises, yet potentially harboring the same fundamental processes that shaped our own planet and may have given rise to life itself. This is the current frontier of rogue planet research, a field that combines cutting-edge observational astronomy, sophisticated theoretical modeling, and profound questions about the nature of planetary habitability. As our detection methods improve and our theoretical understanding deepens, we can expect many surprises and discoveries that will continue to reshape our understanding of planets, stars, and the galaxy we call home.